Good morning. Welcome to a new lecture in detection. In this lecture, we will talk about performance of M-ary signaling schemes. In the last lecture, we discussed the performance of binary signaling schemes. So, what is the objective of this lecture? In this lecture, we will learn how to calculate the average symbol error rate of M-ary modulation schemes, and we assume that these signals happen with equal priors. We also sometimes call this average symbol error rate as simply symbol error rate or probability of error. So, I will use these words interchangeably. Okay. So, to start looking into this performance of M-ary signaling schemes, we will take the 4-QAM as the running example. So, in this 4-QAM, we have 4 signal points S1, S2, S3 and S4. To start calculating about this probability of error, we will first calculate what is the probability of error given that we have transmitted signal S1. Okay. So, suppose we have transmitted signal S1, what is the probability of error in that case? Also, you can look in this picture, we have shown NC and NS, these are the noise random variables corresponding to I and Q channel. Okay. So, NC is the noise random variable in the I channel and NS is the noise random variable in the Q channel, and we have assumed that this noise rides on this signal S1 when signal S1 is transmitted. So, first let us look into the decision region of the signal S1. How do we calculate the decision region of the signal S1? So, to calculate that, you have to draw lines from S1 connecting all other signal points. So, we have this is signal S2, this is signal S3 and this is signal S4. So, first step is that you draw lines from S1 to S4 to S3 and to S2. Okay. Once you have made these lines, so the next step is to draw perpendicular bisectors for this line. So, this is the perpendicular bisector to the line connecting S1 and S4. This is the perpendicular bisector for the line connecting S3 and S1, and this is the perpendicular bisector for the line connecting S1 and S2, right. And decision regions is governed by these perpendicular bisectors. So, now you can see clearly that the decision region of signal S1 is simply the first quadrant. This perpendicular bisector is not influencing the choice of decision region of S1. So, decision region of S1 is simply the first quadrant, and it is also very simple to see this. For example, if a received point lies in the first quadrant, this received point will be closest to S1 and thus the detector will decide for S1, right. Okay. So, Y let us say is the received quantity and this is S1, the signal transmitted plus noise riding on the signal. What is the location of S1? S1 is located at d by 2 and d by 2. So, it is d by 2 in the x direction and d by 2 in the y direction, and this random variable NC adds to this d by 2 in the x direction or in the I channel, and this random variable NS adds to this d by 2 in the y direction or in the Q channel. Okay. Now, when will an error happen? An error will happen when the received number will slip out of this first quadrant. So, it might go either to second, third or fourth quadrant. If the received number slips out of the first quadrant, then an error will happen. And when will the received number or observation slip out of the first quadrant? This will be when NC plus d by 2 that is the value of the received observation in the x direction, is less than 0, or ns plus d by 2 becomes less than 0. So, probability of error given that we have transmitted signal S1, there will be an error when the received observation will slip out of the first quadrant, and this will happen when this is true or this is true, and hence the probability of error given that we have transmitted S1 is simply obtained by calculating the probability of these two events. So, probability of NC plus D by 2 less than 0 or NS plus D by 2 less than 0 is simply probability of NC plus D by 2 being less than 0 plus probability of NS plus D by 2 being less than 0 minus probability of NC plus D by 2 being less than 0 and probability of NS plus D by 2 being less than 0. Let us understand why is this. So, look at this constellation again. So, what we are saying is we are transmitting signal S1, and if this observation lies in this first quadrant, then the receiver will detect signal S1. This received value will slip out of this first quadrant when the noise amplitude NC becomes less than d by 2. When this will happen, the received value will lie to the left of this y axis. Okay. So, when NC plus d by 2 is less than 0, the received value will slip to the left of this axis. Similarly, when NS plus d by 2 is less than 0, the received value will slip below this axis, below x axis. And thus, you see when this event happens, the received value will lie either in the second quadrant or in the third quadrant. When this event happens, the received value will lie either in the third quadrant or in the fourth quadrant. So, this corresponds to the received value lying either in the second or third quadrant. This event corresponds to the received value lying either in the third or fourth quadrant. Now, we are calculating the probability of the received value being in third quadrant twice, and thus you have to subtract the probability that received value is in the third quadrant. Okay. And what is that probability? The probability that received value is in the third quadrant is simply the probability that NS plus d by 2 is less than 0, and at the same time NC plus d by 2 is also less than 0. When these two events happen at the same time, then the received value will lie in the third quadrant. And thus, to calculate the probability of error given S1 from these two events, we have to subtract this probability. All right. So, we get that the probability of error given that S1 is transmitted is probability that NC is less than minus d by 2 and NS is less than minus d by 2 minus probability that NC is less than minus d by 2 and probability that NS is less than minus d by 2. Let us see what is this probability in terms of Q function. So, first let us look at a picture. So, let us simply assume that we have two signals 1 and 2, and these two signals are separated by a distance of t. And let us assume that we are transmitting signal 1. And when will an error happen? Error will happen when the noise amplitudes become larger than d by 2. Okay. So, you are transmitting this signal, perpendicular bisector will be at d by 2 from this place. If the noise amplitudes become larger than d by 2, then the received value will lie to the right of this perpendicular bisector and the detector will assume that the transmitted hypothesis is 2. So, an error will happen when NC becomes larger than d by 2, and we know that this random variable is a Gaussian random variable with mean 0 and a variance of sigma square, and we know how to calculate the probability of this event in terms of Q function. So, we have seen before that if you have to look about the probability of a Gaussian random variable taking a value greater than x, then you can easily calculate this probability in terms of Q function, and this will be Q of x minus mean of this random variable divided by standard deviation of this random variable. We have seen in one of the lecture that this can be simply calculated in terms of Q function like this. Here NC is also a Gaussian random variable. So, to calculate this probability, it will be Q of what is x in here, x is d by 2 minus mean, what is the mean of this is 0, and what is the standard deviation is sigma. Okay. So, the probability of this event is simply Q of d by 2 sigma. Why we are stressing so much on this? Because we will get these kind of expressions, and from now onwards I will simply write that probability of NC greater than d by 2 is simply Q of d by 2 sigma. So, now you must know this. Similarly, if I have to find what is the probability of NC less than minus d by 2, so the probability of this event can be understood as 1 minus probability of NC greater than minus d by 2, because either the numerical value of random variable will be less than minus d by 2 or it will be greater than minus d by 2, and the sum of these two probabilities should be 1. So, probability of NC being less than minus d by 2 is simply 1 minus probability of NC greater than minus d by 2. And what is this? By using the same logic, I can write that this is simply 1 minus Q of minus d by 2 sigma, x is minus d by 2 here. And we can use one property that Q of minus x is simply 1 minus Q of x. Okay. So, using this property I can write that this is 1 minus Q of d by 2 sigma, and this is simply Q of d by 2 sigma. Hence, in nutshell, probability of NC greater than d by 2 is Q of d by 2 sigma, and probability of NC being less than minus d by 2 is also Q of d by 2 sigma. And why is this so? Because these random variables are Gaussian random variables, and if they are 0 mean, they are symmetric about 0, and hence the probability of noise amplitudes being less than minus d by 2 or being greater than d by 2 must be same. Okay. So, let us now get back to this equation. So, we have been investigating the probability of error given S1, and now we clearly understand how to calculate this probability. This is simply Q of d by 2 sigma. And what is this? This is also Q of d by 2 sigma, because this random variable is also with 0 mean and has a variance of sigma square. And what is this probability? It is nothing but it is Q square of d by 2 sigma, and hence probability of error given that you have transmitted S1 is simply this. Okay. Now, but we have to find probability of error, right, average symbol error rate. Now, we have found out what is the error rate given that we have transmitted S1, but from here we have to go to find out the average symbol error rate. Okay. Now, because this 4-QAM is a symmetric constellation, so you can easily work out that probability of error given S1 will be simply probability of error given S2 will be same as probability of error given S3 will be same as probability of error given S4, right. All signals are symmetric to each other, right. The average probability of error will simply be 1 by 4 times the sum of these probabilities, and because all these probabilities are same, you can simply get that the probability of error is simply probability of error given S1, and hence the overall probability of error is also 2 q of d by 2 sigma minus q square d by 2 sigma. Okay. So, average symbol error rate is the same as the error rate when you have transmitted one of the signal. So, we have got this expression of average symbol error rate in terms of q function and d by 2 sigma, and as before, now the idea is to express this in terms of root of Epno, right. We are interested in doing so, and d by 2 sigma, same as in the case of binary signaling schemes, is simply a square root of eta p, where eta p is power efficiency times Epno by 2. Okay. So, d by 2 sigma is the square root of power efficiency multiplied by Epno by 2. So, if I have to write this in terms of Epno, it is simply 2 q function of root eta p Epno by 2 minus q square of root of eta p Epno by 2. And you know that this is a pretty small number, because the probability of errors that we are interested in is 10 to the power minus 8 or 10 to the power minus 3 or a number like that, and hence this q function typically should give us a value like 10 to the power minus 5, 4 or something in that order, and q square will thus be a pretty small number compared to q, and hence you can safely ignore this, and you can arrive that the probability of error is approximately 2 q of under root of eta p Epno by 2. The next job remains is to calculate the power efficiency for M-QAM modulation scheme. Okay. That is what we are up to. So, now we will be finding out the power efficiency of M-QAM modulation scheme. Now, this power efficiency is simply d square by E b, right. This we have seen in the binary signaling schemes. And what is this E b? E b is E s by log to m. So, E s is the average symbol energy and E b is the average bit energy. Sometimes I also call this average bit energy as bit energy, because it is obvious that we are only interested in average quantities, right. So, this average bit energy should be number of bits in a symbol. So, average bit energy multiplied by number of bits in a symbol should give me average symbol energy or signal energy, and thus average bit energy is average symbol energy divided by number of bits in a signal, and number of bits in a signal or a symbol is simply log to m, right. If m is the number of signals that we have, the number of bits that are required to represent these m signals is simply log to m. So, average bit energy is average symbol energy divided by log to m. So, eta p power efficiency is simply d square times log to m divided by average symbol energy, and now we are good to go. Also remember this formula, because we will be kind of using it several times in this lecture. So, power efficiency is d square log to m divided by average symbol energy, and for QAM we have already calculated the average symbol energy I think in lecture 26 or 27. And we can use that average symbol energy relationship now to calculate this power efficiency in case of M-QAM, which is 6 times log 2 m divided by m minus 1. One immediate thing that you should notice now, and we will talk about this later as well, that this power efficiency decreases with m. So, if we are interested in the power efficiency for a given constellation, this power efficiency decreases with m. Thus, the modulation schemes becomes less and less power efficient as you increase the number of symbols in the constellation. Okay. So, for M-QAM, power efficiency decreases with m, but if you remember, the spectral efficiency of M-QAM increased with m. So, if you wanted a modulation scheme with a larger spectral efficiency, you should increase m, but then what it will do is it will reduce the power efficiency of your modulation scheme. All right, we will talk about this point in lot more detail later on in this lecture. So, probability of error for 4-QAM, we have calculated this as this, and now the job remains to plug in this value of power efficiency, which you can easily calculate by using this relationship. So, this will be 6 times 2 divided by 3, which is 4, and now you can get easily the formula for probability of error for 4-QAM, which is this. So, you plug the value 4 in this relationship, and you can also approximately calculate it like this. Important point that you have to notice now as well, that the power efficiency of 4-QAM is same as the power efficiency of BPSK. All right. So, BPSK has the same power efficiency as 4-QAM. All right. So, we have been able to calculate the probability of error for 4-QAM, right, and we have understood few concepts while doing this evaluation. Now, the question is, what happens as you increase the number of symbols in the QAM? So, we still will continue with QAM, and we will like to understand what happens when you have large constellation. For example, what happens when you go to 16 QAM or to 64 QAM or to 128 QAM whatsoever. So, in case of large constellations, exact formulation of probability of error might not be possible, and what will then be possible is to calculate this probability of error using some bounds or using some approximations, but exact calculations of probability of error will not be possible. And now, we will learn about these bounds and approximations that you can use to calculate the probability of error for large constellations. And the first bound that we will study is union bound. Union bound gives us the maximum bound on error probability, and this union bound is simply calculating the error probability by summing up the error probability due to all neighboring symbols. And it is best to look at an example to understand what I mean. Suppose you want to use this union bound approach to calculate the probability of error given that you have transmitted S1. So, given that we have transmitted S1, what is the probability of error in that case? So, to estimate this probability of error, you have to look at neighbors one by one. So, first you look at the neighbor S2 and you find out what is the probability of error due to this S2, and this probability of error is simply Q of D 1 2 divided by 2 sigma, where D1 2 represents the distance between 1 and 2. Of course, we know that this is D, but we are trying to generalize this stuff. So, remember if the two signals are separated by a distance d, for the probability of error the noise amplitude should be larger than d by 2, and we have already evaluated that this will be q of d by 2 sigma, right, and that is why we worked for a minute or so in deriving this. So, we can use these expressions now seamlessly. Okay. So, probability of error because of this S 2 is simply q of d 1 2 by 2 sigma. Probability of error due to this S 3 is q d 1 3 by 2 sigma. Probability of error due to this S 4 is q d 1 4 by 2 sigma. So, what we are doing is we are looking at a neighbor one by one, and we calculate the probability of error due to each neighbor, and then we sum up these probability of errors, and then we get probability of error given that we have transmitted a signal. And what is d 1 2? d 1 2 in this case is d, d 1 3 is root 2 d, and d 1 4 is d for 4-QAM, a regular 4-QAM constellation. And hence we have been able to predict probability of error given S 1 by summing up these probabilities. And remember, this gives us an upper bound on the probability of error, meaning that the probability of error cannot exceed this, right, but it will be less than this. Okay. So, it is a bound, it is not giving you an exact formula for probability of error. And we can collect these two terms, and we can write that this probability of error given S 1 is simply less than 2 times q of d by 2 sigma plus q of d by root 2 sigma, and of course, you can also write this in terms of M-nose. Okay. And then you get probability of error given S 1 simply by this. So, this is the probability of error given S 1, and how can I think about probability of error, average probability of error, and this will be simply probability of error given S 1, because again we are interested in a regular constellation. So, probability of error given S 1 will be same as probability of error given S 2, will be same as probability of error given S 3, will be same as probability of error given S 4, and thus the average probability of error will be same as probability of error given S 1. Okay. So, we have got the upper bound for this probability of error by using union bound. Before proceeding further, let us stop for a minute and let us try to identify why this union bound gives us an upper estimate of the probability of error. And to think about that issue, let us see what is happening. When we are calculating the probability of error due to S 2 alone, we will require that the NC should be less than minus d by 2. So, when we are saying that NC should be less than minus d by 2, we are covering the second and third quadrant. Okay. So, probability of error due to S 2 would be given by this condition, and probability of error due to S 4 will similarly be given by this condition. And when we use this condition, we are already covering the third and fourth quadrant. And now, when we think about this probability of error due to S 3, actually you want that this NC should be less than minus d by 2 and NS should be less than minus d by 2, but you have already covered third quadrant twice, and you are adding again the probability of received value to lie in the third quadrant, and thus you are recounting events, okay, and thus the union bound gives you an upper estimate of the probability of error. Okay. So, just revise this, this will give me the probability that received value lie in either second or third quadrant, this will give me the probability that received value will lie either in the third or fourth quadrant, and this will give me the probability that the received value will lie in the third quadrant, and you know that you have calculated the probability of received value to lie in the third quadrant way too many times, and thus this probability of error will actually be much more than the actual probability of error, and thus union bound is not at all a tight bound, right, and you can use a better bound than the union bound, which we call as the intelligent union bound. So, let us look at this intelligent union bound, and what does this intelligent union bound do is this makes the bound little bit more tighter. So, what it says is in this summation you should only include the signals which are influencing the decision region of the considered signal. For example, if we are considering a signal S1, so we are assuming that signal S1 is transmitted and we want to calculate the probability of error in that case, then you should only consider the signals contribution to the error as the signals which are influencing the decision region for the signal S1. So, the first question is how do we calculate the decision region, and the idea is same as before. You start by drawing lines to all signals from S1. So, we are now calculating the decision region for S1. So, we have to draw lines from S1 towards all signal, and then the second step is to draw perpendicular bisectors to those lines. So, this is the perpendicular bisector for the line connecting S1 and S2. This is the perpendicular bisector for the line connecting S1 and S3. This is the perpendicular bisector for the line connecting S1 and S4, and this is the perpendicular bisector for line connecting S1 and S5, and this is the perpendicular bisector for the line connecting S1 and S6. Now, you know that this perpendicular bisector is not influencing the decision region of S1, and hence this signal S6 can be ignored when you are calculating the probability of error when S1 is transmitted. That is it. Okay. So, in this summation you should ignore, or you should only consider the signals which are influencing the decision region of the considered signal. Let us quickly see this with an example. So, if we have to evaluate the probability of error given S1 and the constellation is this, then when we are doing the union bound approach, we have to have the contributions from all neighbors. So, from 2, from 3rd, from 4th, from 5th and from 6th. What when you are doing intelligent union bound, because the signal 6 was not influencing the decision region of S1, you can ignore this term in intelligent union bound. So, intelligent union bound makes the bound little bit more tighter by pruning the terms which are irrelevant. So, it has got rid of this term, and thus the probability of error given S1 will be lesser in this case compared to this case. Okay. This is still an upper bound, right. So, the probability of error will still be less than this, because you will be counting few terms twice again in here. Okay. So, now from bounds we are going to approximation, and this is nearest neighbors approximation, probably one of the most widely used approximation when you are calculating the probability of error. And what is this? It can be used for regular constellations. So, normally we will deal with regular constellations only, right. The signal set will be regular constellations. So, for PSK the symbols will lie on a circle, for QAM the signals will lie on a rectangle. Okay. So, probability of error is approximated as n d minimum times q of d min by 2 sigma. So, first let us define d min. D min is the minimum distance between two signals in a constellation. For example, if I consider 4 QAM, we know that these signals lie at the minimum distance of d, and the distance between these two signals is larger, root 2 d. Okay. So, there are some signals which lie at a minimum distance, we call that minimum distance as the min, and the number of neighbors of a signal at the minimum distance d min is referred to as number of nearest neighbors. Okay. So, for example, in this 4-QAM, how many nearest neighbors to this symbol? There are 2 nearest neighbors, one this and one this. Okay. Hopefully, now you have understood the meaning of word d min, which is the minimum distance present in a constellation, and n d min is the number of neighbors at that minimum distance d min, and probability of error is simply obtained by this relationship. So, let us work out this 4-QAM. So, let us consider again the probability of error given S1, how many neighbors? 2 neighbors, and what is the d min in this case is simply d. Okay. So, probability of error is this. Now, this matches with intelligent union bound that we have used, and this will be the case for many regular constellations like PSK and for QAM. Okay. So, let us use this nearest neighbors approximation to calculate the probability of error in 16-QAM, and the idea would be to first calculate the number of nearest neighbors, okay, or in fact the average number of nearest neighbors. So, let us first consider these 4 signals in this constellation and how many nearest neighbors this signal has. Okay. So, this signal has 4 nearest neighbors, 1, 2, 3 and 4. Okay. And similarly, this signal will also have 4 nearest neighbors, this signal will also have 4 nearest neighbors, this signal will also have 4 nearest neighbors. So, there are 4 signals with 4 nearest neighbors. Now, you consider these signals, this, this, this and this. These signals on the boundaries will have only 2 nearest neighbors. So, there are 4 signals which have 2 nearest neighbors, and now we have 8 remaining signals. So, 2 here, 2 here, 2 here and 2 here. If you look at these 8 signals, each one of them will have 3 nearest neighbors. So, this will have this, this and this. So, there are 8 signals with 3 nearest neighbors. So, if we want to find the average number of nearest neighbors, this will be 3. And now, the probability of error is straightforward. We know n d minimum for 16-QAM, which is 3, and we have already calculated the power efficiency, which is expressed by this relationship, and for m being 16, this power efficiency turns out to be 8 by 5, and thus the probability of error is approximately 3 times q of root of 4 E b by 5 n naught. Okay. So, calculation was really trivial. You can easily calculate the number of nearest neighbors, and you can easily calculate the power efficiency, and you get an approximated value of probability of error for 16-QAM. Can we generalize this for any M-QAM? We have already generalized the power efficiency for any M-QAM. Now, we want to find or to generalize the n d minimum for any M-QAM. Okay. And of course, we always assume that we have regular QAM constellations. So, if we assume that this has m symbol points, and let us assume that is a square grid constellation, that is usually when we talk about regular QAM structure. So, how many columns we have in here? We have root m columns and we have root m rows. So, if I consider this group, this group of points all will have 4 neighbors, okay. And how many points do we have in this group? So, in this group how many rows we have? We have root m minus 2 rows and we have root m minus 2 columns. So, number of points in this group is simply root m minus 2 square, and all these points have 4 nearest neighbors. Now, you can think about these points. How many points here? Again we have root m minus 2 points in here, and there are 4 such groups. So, one here, one this, one this, and one this. So, you have 4 such group, and each group has root m minus 2 points, and each member of this group will have 3 nearest neighbors. So, we have 3 here. Remaining are these 4 points, the points which are lying at the edge. These 4 points will have only 2 nearest neighbors. So, average number of nearest neighbors can be calculated by carrying out this arithmetic, and you can easily do this yourself, and we get average number of nearest neighbors 4 times 1 minus 1 by root m, and thus the probability of error in M-QAM, where we are assuming square grid constellation. So, the number of bits in a symbol must be even for a square grid constellation. So, if we assume that M-QAM, the probability of error can be calculated like this. So, here we have just substituted for the value of power efficiency as well. So, with this what we have done is we have been able to complete the probability of error expression for M-QAM, and we have also derived the power efficiency for M-QAM. And next is to quickly see the probabilities of errors for PSK and PAM, and then we will make the comparison and will conclude this lecture. So, probability of error in case of PSK using nearest neighbors approximation is again given by this relationship. In PSK the task is easier because average number of nearest neighbors are 2. In fact, every symbol has 2 nearest neighbors. So, one this and one this if you consider this signal, that is easy. What is power efficiency? Power efficiency can also be calculated easily. So, just see that this radius of the circle, though we have done this calculation, but I think it will be worthwhile to relook at it. So, if I consider that the radius of the circle is r, this distance is d by 2. So, r sin theta is d by 2, and sin theta is sin pi by m, where m is the number of points. Okay. Then we know that the power efficiency is d square log 2 m by E s or d square by E b, you can think in any way as you want. We are thinking in this term, and we have already derived this relationship today, and this E s is simply r square, right. So, energy of each point is simply r square. So, we are squaring this up, we get E s, and from this we get the power efficiency as this 4 times sin square pi by m log 2 m, all right. And from this we can calculate the probability of error by substituting the value of n d minimum and substituting the value of power efficiency. So, there is power efficiency by 2, and hence the factor 4 has become a factor 2. Okay. So, calculating the probability of error for PSK was rather trivial, simple, right. In the same spirit, let us calculate the probability of error in M-PAM. Again it is simple. So, power efficiency is d square log to m by E s. E s we have calculated I think in lecture 26, which is this, and power efficiency thus can be easily calculated like this. Okay. And how to calculate this ND minimum in the case of M-PAM? ND minimum can be simply given by this expression. Okay. So, you can think that m minus 2 signals will have 2 neighbors, and the signals at the end of this line, there are 2 signals which will have 1 neighbor. So, average number of neighbors is given by this, which simply simplifies to this thing. Okay. So, probability of error is simply this handy minimum times q function of a square root of e to p abno by 2. So, we have already calculated power efficiency, just plug this in here and you can get the probability of error expression for M-PAM. All right. So, after understanding the probability of error in case of QAM, the probability of error calculation for PSK and for PAM is really simple. So, finally, we compare the performance of these 3 modulation schemes that we have seen, M-QAM, M-PSK and M-PAM. So, these are the power efficiencies of these modulation schemes, and then if we plug in this ND minimum that we have got, multiply with this q of root of e to p abno by 2, we can also arrive at the probability of error expression for these modulation schemes. Okay. So, this just summarizes whatever we have discussed so far. Okay. Now, what I will like to do is let us compare QPSK with 16 QAM and let us see what happens. So, in QPSK we have got this as the probability of error. The number of nearest neighbors in QPSK is 2, right. So, QPSK is same as for QAM, number of nearest neighbors was 2, and then we have this factor in here. Eta p1 represents the power efficiency of QPSK and abno 1 represents the abno of QPSK. Similarly, in case of 16 QAM, the number of nearest neighbors was 3 and we are assuming that it has got a power efficiency of eta p2 and it has got an abno of 2, and we know what is this eta p1 and eta p2. What we want to do is ask the question that when these 2 probabilities of errors should be same, what is the difference in their abnos requirement? That is what we want to see, and we have done such an exercise also for the binary signaling scheme. So, if we want the probability of errors to be same, and this happens given my abno is suitably large. So, I can approximate this function as this function, where same as in the last lecture I am using the relationship that q of x is simply e to the power minus x square by 2 for large x, and thus I can convert this to this expression for large abnos, and thus for these 2 modulation schemes to have the same probability of error, this should be same as this. And if you want this should be same as this, what we want is this expression should be same as this expression. Okay. I have just done some arithmetic, have taken log on both sides, and from that I have got this relationship. Now, this quantity will be much smaller compared to this quantity if I assume abno to be larger, and thus I can ignore this thing, and thus again taking the log I get 10 log abno 1 minus 10 log abno 2 is approximately 10 log eta p2 by eta p1. So, this is the abno requirement in QPSK in dB scale. This is the abno requirement in 16 QAM in dB scale, and this difference in Abno requirement should correspond to the ratios of power efficiency in dB scale. So, eta P2 is 8 by 5, 16 COM power efficiency, and power efficiency of QPSK is 4. Thus, taking this ratio and trying to express this in dB scale, I get a number minus 3.97 dB. Thus, Abno requirement in QPSK systems is minus 3.97 dB smaller than the Abno requirement in 16 COM systems. Thus, QPSK is more power efficient than 16 COM. That is one thing. Second thing is, and quite useful thing, that you can quickly calculate this number by just the ratios of power efficiency, and that is why this power efficiency is so important. Calculation of power efficiency is trivial, it is easy, there are straightforward formulas for that. Once you know these power efficiencies, you can easily calculate their ratios, and you can easily obtain a number which tells you how much one modulation scheme is more power efficient than the another modulation scheme, and this is quite useful. For example, you can compare 16 PSK with 16 COM, calculate the ratios of their power efficiency. 16 COM again has power efficiency of 8 by 5, 16 PSK you can work out by using the formula, it has got a power efficiency of 0.6. You easily calculate the ratio 2.66 and you easily arrive at a number 4.25 dB. That means in 16 PSK the Abno requirement is 4.25 dB larger than the Abno requirement in 16 COM. So, you can easily calculate that. Similarly, you can calculate the 16 PAM efficiency with 16 COM efficiency, and by using the same arithmetic you can arrive to the result that 16 COM requires minus 9.2 dB smaller Abno than 16 PAM. Okay. This is quite useful. Let us look at the same thing graphically. So, first this we have seen before in the modulation lectures. We see that the spectral efficiency of M-QAM increases with M, and that is why we love this M-QAM, because if you want to pack more bit rates per given bandwidth, you should use larger M's. But as soon as I increase this M, what happens in terms of power efficiency? Power efficiency starts to decrease. So, power efficiency of COM, PSK and PAM, all these modulation schemes decreases as you increase M. Of course, for COM the decrease is not so much as in the case of PAM or PSK, and thus we like to use COM. Though I did not mention the spectral efficiency of PSK and PAM in this case, but the spectral efficiency of PAM and PSK at passband will be same as the spectral efficiency of COM. Okay. All these three modulation schemes have got the same spectral efficiency, but in terms of power efficiency COM is best. COM has got the largest power efficiency for given M, and thus COM will require the least Abno when you are comparing this COM, this PSK and PAM. We can also plot this power efficiency in dB scale, because this tells you quickly how efficient is one modulation scheme compared to another modulation scheme. For example, in the last lecture on binary modulation scheme, we said that for a bit error rate of 10 to the power minus 8, BPSK requires Abno of 12 dB, and BPSK has got a power efficiency of 4. COM also has got a power efficiency of 4 when you are considering 4 COM. Now, so if we want to find out what Abno 16 COM requires for a bit error rate of 10 to the power minus 8, you can easily deduce this from this figure. So, you see that 16-QAM has 4 dB smaller power efficiency than 4-QAM. Thus, 16-QAM will require 4 dB larger EBNO than what 4-QAM required. So, EBNO requirement in 16-QAM is 16 dB. Okay. So, you can quickly calculate and tell these numbers. Okay. Let us look at some other calculations, quick calculations. For example, BPSK we said required EBNO of 12 dB. It has got a power efficiency of 4 or 6 dB. In dB it is 6, in numbers it is 4. 16-QAM has got a 4 dB lower power efficiency, and thus it will typically require 16 dB EBNO to have a bit error rate of 10 to the power minus 8. 16 PSK has again a 4 dB approximately, these are approximate numbers, 4 dB smaller power efficiency than 16-QAM, and hence it will require an EBNO of 20 dB to have a bit error rate of 10 to the power minus 8. 16 PAM power efficiency was 9 dB smaller than that of 16-QAM, and thus it will typically require an EBNO of 25 dB to have a bit error rate of 10 to the power minus 8. And if you look at these probability of error graphs versus EBNO, you get the same numbers almost. So, QPSK, BPSK are around 12 dB, 16-QAMs 16 dB, 16 PSK little bit higher than 20 dB, and 16 PAM little bit higher than 25 dB. But what EBNO it will require for probability of error of 10 to the power minus 8 can be easily calculated by this ratio of power efficiencies, okay? And this is what we are stressing on. So, in this lecture we have completed the analysis of probability of error for spectrally efficient modulation schemes like QAM, PAM and PSK, and in the next lecture we will look into the probability of error for orthogonal modulation schemes. Remember, the main difference between orthogonal modulation schemes and the modulation schemes that we have seen today is that in orthogonal modulation schemes the power efficiency increases as we increase M, right, because orthogonal modulation schemes are optimized to harness power efficiency. Thank you.